Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to take a look at a 4000 series CMOS chip. In this case it's the 4007, and I think it's probably fair to say that out of all the various types of 4000 series chips that there are, this one is probably the simplest and probably the most basic, and arguably extremely versatile, since it's quite a good set of building blocks. So let's start by reminding ourselves what and why CMOS is all about. Okay, we'll start with a reminder of what CMOS is. Complementary metal oxide semiconductor is what the name stands for, and it's pairs of N and P channel transistors in an arrangement a little bit like this. This is one of the diagrams from the data sheet, but you get the general idea. And the whole point of having a complementary pair, N channel and P channel, is that one transistor will always be off, and that means there will be less power consumption, and compared to NMOS or TTL, which preceded that, CMOS will always use less power. Less power, of course, means less heat produced, which means you can pack a few more transistors into the same space without thermal problems. And obviously less power used means your mobile phone battery lasts a bit longer, or whatever bit of battery powered tech it is that you've got. So that's CMOS. The 4007 is an interesting member of the 4000 series CMOS, in that it doesn't contain a set of gates or anything. It's a 14-pin dual inline package, and it contains 6 transistors, 3 complementary pairs of P and N transistors, and it's as simple as that. It's not quite as basic as the National Semiconductor diagram says, because the if you look on the TI data sheet, you see that includes the static protection diodes, of which there are many, but they don't affect the function of the transistors particularly. So yeah, there's a bit more going on, but for clarity, it's essentially 6 pairs of transistors. Sorry, 3 pairs of transistors. So what can we do with it? Well, many things. Let's have a look at a very straightforward thing, which is an inverter. So if we feed an input into one of the transistor pairs and take an output from the 2 outputs, you can see the pin numbers on the chip there, and that gives us an inverter, or a NOT gate if you like. So if input is low, output will be high, and if input is high, output will be low. So let's have a look what that might look like on the breadboard. My example here, I've got an LED at the output there, with a resistor to stop the LED committing carry, and then I've got a push button switch. So the input is being held high through a 1K resistor, and when I press the push button, that swings it low. So let's go and have a look at that on the bench. Okay, here's the gate then, exactly as described just now on the slide. So I'm just using one of the pairs from the transistor. So I've got power supply here and here. The output I've got going to this LED, and there's a current limiting resistor here to protect the LED from committing carry, and then the input goes along there from that 1K resistor, which is pulling the input up to logic high, and it's a NOT gate, in other words an inverter. So I would expect when the output is high, which it is at the moment, that LED to be not lit. And this push button switch, which I've just managed to pull out, this push button switch simply grounds that input and takes it low. So if I press that, the LED lights, and if I loose it again, LED goes out. So that's logic high input, logic low output, logic low input, logic high output. So it is indeed acting as a NOT gate. Now that's a fairly crude test. Let's now look at something a little bit more complicated, where we feed a triangle wave into the chip and see what happens there. Okay, here I am reconfigured then to look at the input and output of the transistors on a scope. So I've got here attached to a signal generator producing a triangle wave, and if we have a look at the trace we're going to get from the triangle wave, it looks like that. It's actually 5 volts, and it's 5 volts from the line there up to the top. So we're in DC coupling here. If I do it to AC, you'll see what I mean. So we're DC coupled, so the voltage rises from 0 to 5 and back again, and I'm just at 500 Hertz for no other reason than it just worked that way. So I've got the second trace hooked up to the output of the gate. So let's see what it makes of it. And there you can see there, yes, we have indeed got inversion. That's high when that's low, that's low when that's high, and you can see the cutoff. These are both the same volts per division, by the way. So we've got about 5 volts there, a bit less there, and you can see the cutoff is occurring roughly halfway up. So it rises gently, and then at about 2.5 volts it kicks in, fully triggered, so to speak, and then as the voltage drops back down, it's at the same place really. Now if I just increase the volts per division a little bit and just bring that down so you can see it, it appears to have vanished simply because this is an analog scope. It traces there, but you can see it is maybe just over 2.5 volts, something like that, it's flicking over for between low and high. So there we go. That's clearly not, well, we're certainly getting inversion, but it clearly isn't as clean as it might be. So we'll just have a quick look now at the same arrangement, but using the 4049, which is indeed a hex inverter. Okay, reconfigured here. We've got the 4049 CMOS hex inverter. Interestingly enough, on the 4049, the positive rail goes to pin 1, and not the top left-hand pin like you'd normally expect. Ground is still the same though on the end pin. So I've got exactly the same triangle wave feeding into one of the gates, and I've got the outputs attached to the second gate. Now if you're now screaming at the screen that I'm running a CMOS chip without doing something with all the spare inputs, yes, I know, just try and breathe normally, it'll be fine. No hex inverters were harmed in this process. Let's just now switch on the second trace and see what the output looks like, and as you can see, it's very different to the 2 transistor version. Yeah, we've got inversion and it isn't exactly the same, but we've most definitely got it flipping from 0 up to 5 and back. So the rise time and the fall time of the inverted output are a great deal more square than they were on the previous version. So clearly there's more to an inverter than just a couple of CMOS transistors. I think we knew that really, but and of course the Schmitt trigger is different yet again. So there you go, that's 4007 an inverter and a 4049 on one of the inverter gates. So let's see if we can make ourselves a better version, in this case a Schmitt trigger. And to do that we're going to use this circuit found on the Analog Devices wiki web pages, which are very good, definitely worth a visit. If you search 4007 Schmitt trigger, you'll find these pages. They're very good. So we've got input on pins 6 and 10, output on pins 3 and 12, but perhaps hard to spot there is that pins 4 4, 8 and 9 are connected to pins 2, 11 and 13 as well. So on the breadboard that looks something like that. So we're going to feed the signal in on the left there and take it out on the right. So let's go and have a look at that on the breadboard. Okay, here's the 4007 reconfigured as a Schmitt trigger circuit as per the description. I think it's fairly self-explanatory. So I've got signal coming in here and got signal coming out here. So let's go straight to the scope and have a look. And as you can see, we've got a very different kind of arrangement. That's much more like a proper invert. So that the Schmitt trigger function there is working rather well. It's forcing a much faster rise time on the output. So it just goes to show a little bit of reconfiguration with those transistors, and you can easily produce something which is considerably more acceptable. Okay, well there you've got the 4007 and bonus of the 4049 at one point as well. And there's all sorts of things that you can build with those three complementary pairs of transistors. I've just scratched the surface, so maybe it's worth getting hold of one if you can, and maybe having a tinker. I enjoyed reminding myself of a real basic level of understanding of how CMOS works and CMOS integration. So I hope you found that useful. Thanks very much indeed for watching, and I look forward to seeing you on the next video.